This video is about linear approximations and differentials. For our notes, we're going to begin with a diagram, and we have a quadrant 1 picture going on. We're zoomed in on quadrant 1, and I'm going to draw a simple, smooth curve, just kind of cruising right through quadrant 1. It kind of dips down a little bit and then heads back up as x increases here. Then we want to draw a tangent line to this curve. Somewhere that at least visually looks good. It's tangent to the curve. This tangent line I have drawn is in red. And then right where the curve and the tangent line intersect, of course, by definition they intersect at one point if it's a tangent, we're going to call the x value of that point a, and then of course the y value we'll just call f of a. So in other words, the coordinates of this point where the line is tangent to the curve is a, comma, f of a. Now if we bring in some algebra to this picture that we know already, we could say that using what's called point slope form, we could actually come up with an equation for this tangent line. Now we don't have much on this diagram yet, so we're just going to be very general with it. But you may recall point slope form is where we write y minus y1 equals m times x minus x1, where m is the slope and then x1, y1 is a point on the line. Given the context of this diagram, we're going to change a little bit of this notation in the point slope form. So instead of y, I'm going to use capital L of x. Instead of y1, we're going to use f of a. Of course, that's the y coordinate of the point we have on our line drawn above. So we have L of x minus f of a instead of the y minus y1 equals, and then for m, which represents the slope of the line, we could call that f prime of a, which would represent the slope of this tangent line at a, when x is a. And then, of course, we'll finish this off in parentheses by writing x minus a, where really a is like the x1. Okay, so this is familiar as far as the point slope notation, but now we're just slightly changing some of the way we're writing the values of it. If we were to take what we just wrote and simply solve it for the L of x variable that we used in place of the y, then really I would just be adding the f of a to both sides, which would mean that capital L of x equals a positive f of a, since I'm adding it to both sides, plus f prime of a times x minus a. So we're going to add a definition here with what we just wrote, and so in fact we'll box that up, the L of x formula, because L of x is what's called the linearization of f of x at a. We can use it for a linear approximation of f of x at a. And let's go back to the picture to understand how this works. You may have some curve, right? We just drew some general curve here, but that could represent really any function. Perhaps it's hard to compute values of some function out there, and this curve, let's just say, represents it. A polynomial may not be that bad, but let's say it's some really ugly function and we're just, we have this curve to represent that generically. Well, it turns out that if you look at this picture where our tangent line comes through and of course hits the curve at one point and then kind of keeps going, wouldn't it be true to say that if you're close enough to the point, I'll just kind of circle a little region here where we're kind of close to the point, and if you are close enough to it, so the x values are, somewhere surrounding a, then it does appear that the curve is fairly close to the tangent line. The reason that's significant is we could then say, well, I could probably estimate the value of the curve, the function value at the curve, by using the function value at the tangent line. So if I were to find, for instance, the vertical value to the tangent line is really not that far away from the vertical value of the curve, and it may be a lot easier to utilize the tangent line, which is where the idea of using it as a linear approximation came in. Next, let's talk about what are called differentials. And to do so, we're going to recall something. You may recall from derivative notation that f prime of x is one such way to denote a derivative. That's the Newton notation. But we also know that it's equal to dy over dx, and we had a little intro on that being called Leibniz notation. But so far, all we've been using this dy dx as is basically synonymous with f prime of x. We've just said it really just means the derivative with respect to x. That's a way of using this notation which kind of ignores the questions of like, okay, well then what is dy and what is dx? We just kind of use it as one big lump notation representing the derivative. Well, it turns out that the dy and the dx do have their own individual meaning. So if I take this equation, f prime of x equals dy over dx, then that implies if I were to solve for dy, which by the way you could do by simply multiplying by dx on both sides, which would tell you that dy is really just f prime of x times dx. Now you may not have thought to do that if you didn't think of dx as a value that you actually could multiply on both sides by, right? So we haven't been using this notation in this way quite yet, but it is actually part of how this notation works, which is partially why it worked so well for Leibniz when he was developing it. Now we'll add a definition, which is this: dy is a dependent differential and dx is an independent differential. That kind of goes with those variables as we're used to using them. Typically x is the independent variable axis and y is the dependent variable. These values, these dy and dx's, are real number variables. So they're actually just numbers or values. Of course they're variables, but they represent numbers in a fraction. Now to get a better conceptual sense of how these differentials come into play, let's go ahead with another diagram where again we're zoomed in quadrant 1, and this time I'm going to draw another smooth curve that just kind of cruises through the quadrant. I'm going to have this one kind of bending downward as it goes right. It'll just be easier to show the picture this way. We'll again throw a tangent line to our curve. And for this picture, again, we're going to put a point where the tangent line would intersect the curve, but we're just going to give that point a name, just for reference. We're going to call it point P. And then somewhere further down to the right on the curve, I'm going to put another point and call that point Q. The x value beneath the point P that we've drawn, where the curve actually hits the tangent line, we're going to call that x value just x. And then moving down the line where the Q point is, so beneath it, we're going to call that x value x plus delta x. Delta is the Greek letter D. It looks like a triangle. So triangle x really means delta x. It's just some variable. So x plus delta x means something a little more than x. How far more? We don't know. But it's just something further down to the right. That's the x coordinate of Q. Now we're going to add a little bit more to our picture. So right at point Q, which is on our curve, but since the curve was kind of bending downward to the right, the tangent line is now cruising above our curve, which means Q on the curve is below it. So we're going to draw a line segment that goes directly from Q straight up to the tangent line. I'm going to put a point on the tangent line where that little segment would hit it. We'll call that point R, again just for reference. But then beneath Q, we're going to extend a segment down to the place where if you were to draw a right triangle where there's a bottom side from P, which was our original tangent point there, all the way down to where this lower segment would hit beneath Q, we'll call that point capital S. Now this, again, these letters are just for reference so that what I'm saying can make some sense here. But if we understand this diagram now algebraically, Remember that the red tangent line is tangent to the curve, hitting it at point P. And we also know in context that the slope of the tangent line is what we call the derivative. Well, in this picture, you can actually see the slope geometrically. Remember, slope is just rise over run. The rise of this tangent line would now be from point R, which we put where directly above Q, we're hitting the tangent line. So from R all the way down to S, that would be the rise of the tangent line. And so you could call that the dy. The run in this same diagram would be from P to S. So as we're using or used to using rise and run in an algebra class, so run would be like the dx. Now this is making some sense because if I use those two values, which we're now calling differentials, in a fraction form, then really the slope of the tangent line would be rise over run, which would be dy over dx. Well, what do you know? That's the typical derivative notation we've been using from Leibniz. Now let's add a little more notation to this already crowded picture, but it's important to add this. We're going to say that the distance from Q to S, if you have those points drawn as we had them, we're going to call that distance delta y. So delta, again, is the triangle symbol. So delta y is from Q to S. Q is the point on the curve further down from P to the right, but then beneath it is S, which is the corner of this right triangle we have now in our picture. So from Q to S, we're going to call delta y. And then delta x, we're going to just say is the same thing as dx. So that would be the length all the way across the run. With that notation in this diagram, it's now possible to see how it all connects. So let's now, beneath our diagram, write out a limit. And let's say the limit as delta x approaches 0. Okay, so now keep in mind where or what delta x is. We've used a couple different places labeling it where the x value of point Q that we labeled down the x-axis, remember that was x plus delta x. So when we did derivatives already, we often used like an x plus h. Well, some authors actually use delta x instead of h. It's just a preference thing. The point is, delta x is some small value that when you add to x moves you further down the axis. So we can imagine that value approaching 0 would mean that this second point is kind of working its way to the left toward the x place, right? So the x plus delta x is getting closer to the x as delta x gets smaller. You're simply adding less and less to x, which means you're getting further to the left, closer to where x was. So that's what's happening with the limit as we take it as delta x approaches 0. Now what we want to write is the limit of delta y over delta x. Now if you go back to what the diagram said about delta y and delta x, as we move our way to the left toward x as delta x is approaching 0, then consider delta y being this vertical. I'm just going to kind of draw some different versions of it in here. So delta y is a vertical segment between the base of our triangle and the curve. Delta x would be from where that hits the base of the triangle all the way to point P. Well, if you kind of keep reimagining where those are, if I drew just a line segment for delta y and delta x, and then connected that triangle to find a slope, it would be getting close to our actual tangent line, but maybe not quite it. If I move further down, the closer I get where delta x is approaching 0, then again, drawing a slope using those rises and runs, delta y and delta x, is going to give us a line that's closer and closer to the actual tangent line. In fact, as we get really close to where point P is, you can see the picture's all kind of closing in, and the slope of this now light blue line where we're approximating with a rise over run of delta y over delta x is getting pretty close to the actual red tangent line we have here, which means we can say that the limit as delta x approaches 0 of delta y over delta x is dy over dx, which of course is the slope of this tangent line. Of course, that's our derivative notation. So this turns out to be a significant connection to understand how all these pieces fit together. And it makes a lot more life or sense out of this dy dx notation that we've been using for derivatives. It's fine to think of it as just a derivative, but to understand the differentials as values, a rise and a run, or at least the limit of those, makes a lot more sense. Let's try an example where we want to find the linearization for f of x equals sine of x at a equals pi over 6. Well, let's recall from our notes above that we have a formula for linearization. This is the capital L of x, and we solved for it from the point slope form, and it ended up as f of a plus f prime of a times x minus a. Now, in our case, we actually have f, it's given as sine of x, and we have a, it's given as pi over 6. So really we're just kind of plugging stuff in, which means we could say L of x equals f of a, that's, well, sine of pi over 6. We're just plugging in the value given for it, plus f prime of a. Well, f is sine, so f prime would be cosine. And of course, we still want a as the input, so cosine of pi over 6. And then we're multiplying by x minus a, which would be x minus pi over 6. Now we can turn some of these into nicer values, like sine of pi over 6 is really 1/2, plus, and then cosine of pi over 6 would be root 3 over 2. I have to dust off that unit circle to be confident with those. And then x minus pi over 6 could just stay as it is. So this really is the equation of the line that could be used to approximate this function near a being pi over 6. Let's try another example. This one says the radius of a circular disk is given as 24 centimeters with a maximum error in measurement of 0.2 centimeters. We want to do a couple things. The first is use differentials to estimate the maximum error in the calculated area of the disk. Okay, so let's get a couple things going here. First of all, let's recall that if this is a circular disk, the area of a circle is pi r squared, where r is the radius. Now, we have to understand the context as well. If we're trying to use differentials to get this estimate, I think a picture is sometimes helpful. Notice that if our area formula is pi r squared, that's actually a squared that's a parabola. So even our picture could be fairly accurate. If we just draw some, roughly parabola looking thing, I'm focusing in on quadrant 1 because we're talking about positive values here. And then we're going to put the given value for this radius, which is 24, that's provided in the problem, on the x-axis, and then directly above that, so where f of 24 would be on this curve, or you could say a of 24, we're going to put a point on our curve there, and then we're going to estimate a tangent line to the curve right at that point. So really the x-axis in our little diagram is, we could call it the r-axis. It's like for various radius measurements. And then the function, the y-axis or the curve itself, you could call a of r. That's the actual area you get from any given radius according to the formula. Now we were also told that the maximum error in the measurement was 0.2 centimeters. So to illustrate this, let's go to our picture here, and then somewhere down further to the right, so past 24, which we've already marked on here, to the right, we're going to put 24.2, which would be adding the 0.2 centimeters of error, and we're going to call that distance. If you go back to our diagram above, then you'll recall that that difference or distance between what this problem says is the given radius, and then of course these possible error of 24.2. We're going to call that value our dr value, which of course would be the same thing as delta r. If you go back up to our diagram above, you can see those, we were using x's up there, but same kind of thing. And by the way, you may be wondering, well, okay, what if the error is on the left side, right? This is 0.2 bigger than 24. How about 0.2 less than? Well, actually, which side you use for the diagram won't even matter, as you will see shortly. We're just kind of understanding all the pieces and how they fit together with as simple of a picture as we can get. Now, if you go directly above the 24.2 and find the place on the tangent line where that would be, I'm going to put a point on the tangent line directly above 24.2, then you can make this start to look like the diagram we had above. I can add in the segments to create the triangle and all the different places we have there, and we can label it more importantly in the following. Now, it is important to note that this particular diagram we're drawing for this problem is different from the one we have above in our notes, because this is an increasing function and our tangent line is kind of passing beneath the curve, which is going to change a little bit of the labeling, but the identities are still the same thing in that really the slope of the tangent line, that's the dy dx. Well, in this case, that's dA over dr, so the dA value should really be the shorter segment from the point on the tangent line down to the bottom of the triangle. That's the rise of the tangent line slope, so to speak. And then the run is already labeled down below as dr. That's just the distance all the way across. So we can keep that in mind, which means then the distance from that bottom point of the triangle all the way up to the point directly above it that actually hits the curve, that's going to be our delta A, and of course delta R is also labeled the same thing as dr below. This is a convenient and useful way to label a picture in this kind of scenario where you're trying to use the differentials to approximate things. Now what we'd really like is a way to tie together all of these labels that we have in our diagram, and we can do that with really one basic step. If you go back up to our formula for area, which is how this problem is set up, we're talking about the areas of circular disks, and just take the derivative of it with respect to r, the independent variable in this case. So I want d dr of both sides of our area formula, so I have d over dr of A equals d over dr of pi r squared, the right side of our formula. And then if we just take the derivative of both sides, knowing that A is really a function of r, as we have labeled in our diagram, then we really get dA dr on the left side equals, and now r is our independent variable, and I want d over dr of pi r squared. Well, that'd be like saying d over dx of pi x squared. The point is, you can use the derivative rules as we have them. So I'll use the power rule down in front to make this 2 pi and then dr to the first, which you don't have to write. So really dA over dr equals 2 pi r. And then you can simply multiply both sides by dr, as we saw above in our notes, to get dA equals 2 pi r dr. Now this is useful because dA, which we now have alone in our equation, comes directly from the diagram. That was the rise for the tangent line. The tangent line has a slope rise over run. dA is its rise, as shown in the diagram, and that can help calculate the error or estimate the error. The radius is supposed to be 24. It's reported as such, but of course if it's a little bigger or a little smaller, then you're going to get a different area measure for this disk. dA will approximate this for us by plugging in the values we know. So r, of course, that's the value that the radius is supposed to be, so 24. dr was given as 0.2, and that goes back to why it doesn't matter which side of the actual 24 value our diagram showed. I put 24.2, we could have put 23.8. In the formula itself here, we're just putting the 0.2 value. It doesn't really matter which side it's on. The diagram just had to look clear enough. Crunching out this number on a calculator should give us approximately 30.16 centimeters squared as our approximate error. Now the second question in this problem says, what is the relative error and what is the percentage error, which are really the same thing. So you could say that delta A over A. So the delta A is the actual maximum error in the area measurement, over A represents the actual area, and we can say that is approximated by dA over A, because of course dA can approximate delta A as we've been seeing. But these are values we can compute algebraically. We could say dA, which we just solved, what we found for dA above is now going to be used. We said dA was 2 pi r dr, and then A, that's just pi r squared, the actual area. If we simplify this algebraically, we'll simply get 2 dr over r, which for this example, plugging in dr as 0.2 and r as 24, should give us 1 over 60, which as a percent is approximately 1.6%.